Welcome to the Explainer. Today, we're diving straight into Yining Wu's 2026 paper, Active Finite Distinction Systems, a formal core for boundary maintenance under finite capacity. Now, for technically literate researchers working across AI, complexity theory, and systems physics, this paper offers something that is actually quite rare, a serious, restrained, and purely formal research program. There's no hype here. There are no grandiose claims about suddenly solving the nature of consciousness or the origins of life. Instead, Wu establishes a rigorous, falsifiable mathematical core that details exactly what a finite system has to pay in order to maintain its boundary.
Here is our roadmap for today. We'll start with the finite distinction problem, move into formalizing the capacity deficit, then look at complexity and physical dissipation, explore invariant-supported persistence, and finally wrap up with limits and quarantined applications. Let's get right into it.
Section 1. The finite distinction problem. We've got to start with a pretty stark question. Think about it. How does any system, whether it's biological, artificial, or just purely physical, how does it maintain its operational boundary when it mathematically cannot represent everything around it? It's simply impossible for finite systems to maintain unlimited distinctions. The universe is endlessly detailed, right? But an agent's memory, its energy, its processing time, they are all strictly bounded. And this mismatch? It's absolutely crucial, whether you're studying the homeostasis of a single cell, tuning the parameters of a huge language model, or just looking at the structural stability of a complex organization. To tackle this without falling into that vague philosophical trap of talking about observers or agency, the paper lays down a rock-solid formal definition, the Active Finite Distinction System, or FDS. An FDS is strictly defined as a finite capacity system that maintains an operational boundary through state-dependent updates, all under specific resource constraints. Basically, if a system is just sitting there passively like a rock, it doesn't qualify. It has to be actively updating to maintain its boundary. And the system is rigorously pinned down by this 12-component tuple. You've got your state spaces, X for the internal state, E for the environment, B for the boundary, and M for memory. Then the active dynamics, Y for observations, A for actions, U for the update rule, and pi for coarse graining. And critically, we have the operational constraints, a loss function, L, a resource budget, phi, perturbation families, P, and an update timescale, tau. By formalizing this entire tuple, the author is forcing us to explicitly account for every single functional role. Literally no hidden assumptions about memory limits, update vulnerability, or time are allowed here. Moving right along to Section 2, formalizing the capacity deficit. So the crucial takeaway here is this concept of the capacity deficit. Mathematically, we call it delta epsilon. It represents the exact quantifiable gap between the task-relevant rate distortion demand of the environment, that's R min, and the system's strict internal capacity, CS. Look at it this way. If the absolute minimum number of bits you need to predict or control your environment to a certain tolerance exceeds the physical memory capacity of your model space, well, you're in a predictive capacity deficit. You literally do not have the space to map the complexity you are facing. Now, we really need to pivot here and understand a key restraint in Wu's theory. This deficit is strictly about task-relevant demand. It completely avoids the naive trap of suggesting a finite system has to flawlessly represent the entire universe to survive. It doesn't. It only needs to represent the specific environmental statistics that are relevant to keeping its boundary maintenance loss below a tolerated threshold. But here's the kicker. Even for highly specific tasks, this capacity deficit still frequently rears its head. Which brings us to Section 3, complexity and physical dissipation. Because this mathematically unavoidable deficit exists, the system gets locked into this strict, almost punishing chain of consequences. First off, finite capacity forces approximation. Next, because the environment is always throwing persistent novelty at it, those approximations inevitably generate errors. To fix those errors, the system has to update its internal models, and that demands corrective internal complexity. But here's the catch. Updating finite memory requires overwriting old data. That's logical erasure. And implementing that erasure physically, that creates physical dissipation. Eventually, as free energy budgets just run dry, the system hits a hard limit. It has to enter a trichotomy. It either prunes its internal complexity, externalizes its representational load out into the environment, or it collapses entirely. Before we go any further, we have to cross what Wu calls the Landauer bridge. And it's incredibly important to point out that the paper exercises extreme epistemic caution right here. Dissipation claims absolutely require explicit physical bridge assumptions. The paper does not make that blanket, often completely misused claim that every computation universally dissipates kBT ln2 per bit. Logical irreversibility only leads to a thermodynamic dissipation floor if the system is physically coupled to a thermal environment under specific Landauer conditions. If those physical bridge assumptions fail, the thermodynamics fail. But the formal math of the capacity deficit, that remains totally intact.
Okay, let's jump into Section 4, invariant-supported persistence.
So, given this punishing cycle of capacity deficit, inevitable approximation, and physical dissipation we just talked about, how does any structural identity actually manage to persist over time? Well, the answer lies in invariant-supported persistence. Successful systems survive not by stubbornly trying to preserve every single microscopic detail against perturbation, which, by the way, is mathematically and energetically impossible, but by protecting higher-level identity quotients. The system's identity is algebraically protected against admissible perturbations by preserving invariants and symmetries. It basically just ignores the constant scrambling of the microdetails it can't afford to track. Let's see how this algebraic protection operates in real applied systems. Think about error-correcting codes. The logical equivalence class is recovered even if the physical microstates get corrupted. Or look at software API contracts. The system preserves its core function, yielding a consistent response, even as the underlying memory is reallocated or garbage collected under the hood. And in topological systems, winding numbers protect structural gaps against localized noise. In every single one of these cases, a system is preserving its identity by maintaining an invariant quotient.
Finally, we arrive at Section 5, limits and quarantined applications.
The author shows strict epistemic restraint here, explicitly stating that the formal core does not, by itself, independently prove physics, biology, consciousness, or civilization. If you want to study artificial intelligence, you need an explicit AI bridge, defining transient context versus durable memory and proving causal testing. Biological systems, they require specific mappings for metabolism. These domain applications are strictly quarantined. What that means is if a researcher builds a flawed AI model based on this framework, the failure of that specific model doesn't propagate backward to invalidate the formal mathematical theorems of the FDS core.
And this matters deeply for the scientific process. By intentionally separating the formal core from grandiose physical and biological claims, the active finite distinction system acts as a reliable, falsifiable kernel. It sets up this brilliant bedrock foundation for later, rigorous work on AI agency, on how organisms manage the boundary between life and death, on the necessity of forgetting in cognitive systems, and even on the structural limits of organizations. It forces future theorists to explicitly state their variables and their physical bridges.
To conclude our explainer today, I want to leave you with the exact words that anchor this entire theory. The central claim is not that finite systems know everything. It is that any system maintaining a boundary under finite capacity must manage what it cannot afford to distinguish. So as you design your next model or analyze your next complex system, ask yourself, what is the true cost of the boundary you are trying to maintain, and what is your system purposefully blinding itself to just to survive?